This is a demo for STR-validator. In this demo I will show you how to analyze the heterozygous peak balance, the inter-locus balance, Stutter ratios and the sizing precision. The lab has analyzed 165 single-source crime scene samples with the optimal amount of DNA. There was also 8 allelic ladders in this analysis. So first, the result was opened in GeneMapper IDX, and the project was analyzed without using a Stutter filter. The genotypes table was exported, and this is our dataset. Secondly, all samples were reanalyzed using the default Stutter filter, and all the remaining stutters and artifacts were manually removed or corrected, such that only the actual DNA profile remained. The genotypes table was exported again, and this is the reference set with the known profiles. So, I have prepared a folder for validation, and I have copy and paste the icon for the R program into this folder. And to make things simple, I have right-click the icon, and I choose Properties, and make sure that the Start In field is empty. This will make this, the folder I use the working folder in R, so I don't need to look for my data. I can just open the file directly. I have also the exported result from GeneMapper, and it's just a long text file with a lot of columns. We have the reference profile, and I prepared a spreadsheet file for a validation result. So first, open R by double-clicking the icon, and to start we need first to load the STR-validator package. So we type library STR-validator, all lowercase letters without any space or anything. Press enter. Then start the graphical user interface by typing STR-validator and then an empty parenthesis. So this loads the graphical user interface. So you can do everything from here, and the R prompt will be used for messages and error messages or progress messages, but usually we don't need that, so I can minimize the R GUI. So it's more simple to handle this program because it will always have the focus. Okay, so first we have the welcome screen with the general information and links and a license button. We have tabs for different tasks, and the main project window is the workspace tab. Here we can see all the data in our project. So first we start with importing the sample file. Press import. Select a single file for import. We press browse and locate the file. Okay, give it a name. I will just call this validation raw for raw data. Import. Then I will also import the reference samples. Press import, select the file, reference sample, and then I will call this validation ref. So now we can see the two data objects in our workspace, and if we select one, we can press the view button to look at the data. This file is now quite large, so it will take some time to open. Yes, we have 170 samples in 342 columns and over 3000 rows. We can check that the data is correct, and then I will close this. So we need to prepare the data before we can analyze it. So press the Edit tab and then the Trim button. We use this to trim away unwanted columns or samples. So here we have a box for samples and a box for columns. I will select the remove option here, and I will remove positive control, negative controls, and allelic ladders. So we can double click on a sample to put it up here, or we can drag and drop, or we can type. So to be sure to remove all positive controls, I will just write POS, and all negative controls with NEG. The vertical line is the pipe character, and that it's read as OR. So positive or negative or ladder will be removed from the dataset. And that's actually sample names containing the word POS. So it's wildcards on both sides of the word. Then we want to keep just the sample name column, the marker name, all the allele columns. So we adjust we remove the .1 to be able to keep all the allele columns. Die can be useful, and we also want to keep all the heights. Then the program suggests a name. We can change this if we want to. So I will change this to validation sample samples, and then remove the trim. Press the button. So now we can see that we have a new dataset here, and it contains only the samples and columns that we want. But now we also need to make the format long, and I call it slim, because it's not exactly the long format, it's a little bit different. So we select the validation samples dataset, and now STR-validator automatically suggests columns to keep fixed, and that is usually correct, and columns to stack. So we will just overwrite the dataset. Yeah, we accept to overwrite. In each tab there is a edit button on top. Okay, it's the same as view, but you can also edit the data. So and you can use this button on any tab, and you will access all the same data. So if we now view the val samples dataset, we see that it's actually contains only 5 columns and 165 samples, but it's very long now. It's 15,000 rows. So we close this and go back to workspace. So now we should actually do the same with the reference dataset, but I have already prepared that. So this data already looks like the slimmed data. Okay, so we want to start with analyze the stutter percentage. So we go to the stutter tab and click the calculate button. We select a dataset, and that's our validation samples dataset. And then we need to select a reference dataset that is compared to the dataset. So we select the reference here, and that is of course to be able to know what is a real allele and what is a stutter. We will change the default settings to analyze until 2 backward stutters and 1 forward stutter. And we will not accept any overlap between stutter and alleles, because that can give you unusually high stutter values if it's helped by a stutter from a close allele. But that can be interesting to, in some cases, to look at what happens if you allow stutter to interfere with another stutter, like one backward interferes with a forward stutter of another allele. Stutters are calculated by just taking the allele minus the stutter, and that makes some stutter names a little bit strange. So here is a translation table. So for example, if you get a minus 1.9, 1 is the repeat number and 0.9 is the number of base pairs. So if you get a stutter like that, it's actually a minus 1.3 stutter. So this is just a replacement table, and it can be edited by the user, but we just accept the default. And we accept the suggested name and press calculate. So we can plot the data. Click the plot button and select the validation, the stutter result. Now the software tries to automatically detect which kit is used, and usually it does, but if this is not correct, you can manually select the kit. We will just press the ratio versus allele. Now when the software plots the data, the plot will appear inside the Windows R GUI. So we need to open the R window here, and the plot appear. On the x-axis you have the true allele designation, and on the y-axis you have the stutter ratio. And the marker, the plot is by loci. You have the type of stutter, and a -2 means that it's a 2 repeat backward stutter, and a 1 means that it's a +1 stutter or a forward stutter. Then you have the most common stutter is a -1 stutter, but you also have some intermediate stutters. It might be that some of these are actually artifacts of the automated analysis, but when you analyze a lot of data, you will know what's an artifact and what is not by the number of observations. So you can just filter out this at a later stage if you like. Okay, so we can see this the stutter ratio increases by the repeat number as expected, and you also see a lower amount of -2 base pair repeat for the SC33 loci, and lower amount of -2 and +1 stutters. So this is all as expected. We can save this as an image by pressing the Save as Image button. Now by default the software loads the size of the image from the plot device. And I usually uncheck this because I want all images to be of the same size. So I put something that is easy to remember, 30 by 20 for example, because I know this will make a nice plot. I will change the name to Stutter ratio versus allele. The default is format for this image is PDF, and PDF is a vector-based format. So that means it's scalable and you can zoom in without losing any quality. But if you just want to insert the plot into a Word document, you might want to select a common image format like JPEG or PNG, but I will use PDF. And then we check the file path and just save. Now you see that the PDF is appear in the validation folder, and if I open this I get the same plot as before, and I can zoom it without losing any quality. So that's vector-based image format. That's good for publications. Now we can try to plot the ratio versus height. We need to select the RGUI. Okay, so here you have the height of the true allele and the ratio. That can be quite interesting. For example, you see here that most of the time the ratio is quite stable in relation to peak height. So minimize this and we will save this as well. I will change the name to Stutter ratio versus height, and then now it remembers my settings from last time, so I click save. Okay, then the last button here is to summarize the Stutter data in a table format. I click this, select the Stutter result, and for Stutter we would like to get the upper bound, so we would like to calculate the 95th quantile, or that is 95% of the observed data is below this value. So and we want to summarize on a per Stutter basis. You can also summarize per locus or global. If you select global, you will only get one line in the results, so the total overall data. Okay, the name is automatically get appended a table Stutter, and we'll just accept that. Click summarize. Now we can look at the data. Click the edit button, select the table Stutter, and you'll see that we have a column for marker, a column for Stutter type, the number of different alleles that have a stutter, and the number of observed stutters, the mean, standard deviation, 95th percentile, and the maximum value. You can right click a column and sort by decreasing or increasing, and you can also rename a column. In this case I suggest that you actually, to make it more the most simple, you just copy this to clipboard and use an external spreadsheet software to to analyze the data further. So I will copy to clipboard, close this, open the validation spreadsheet file that I have created. Okay, so I will just paste and okay, we can just select the top row and click the data drop down menu and then filter the data using the auto filter. And most common spreadsheet software have this auto filter option. So now you can easily, for example, make a table only showing the one backward stutter value, and you can sort it according to the 95th percentile. So now you see that the D12 locus has the highest stutter percentage. So this you can just copy paste into your validation report or whatever you are working with. So I will save this and exit. Okay, so now for the balance analysis. We press the calculate button in the inter-locus and inter-locus balance group. Select our validation samples dataset and the reference dataset. We can calculate the balance using the high peak divided by the low peak, or the high molecular weight peak divided by the low molecular weight peak. I will just use this. We can calculate the locus, the inter-locus balance as proportional or as normalized values, or we can calculate within each die or globally across all dies. I will select to calculate the balance globally and proportional. So calculate. Okay, so the software warns that we have OL alleles in the dataset, and in case a real allele is designated as OL, that might not work with the balance calculation. In this case, I know we have verified all the results in GeneMapper. So I just click OK. So now we have a balanced dataset. Looks like this. So for each sample and each marker, delta value is calculated. That is the difference between the alleles in number of repeats, the heterozygous balance, the locus balance, the mean peak height, and the total peak height. We can plot these values, select the balance result, and we can plot the heterozygous balance versus the height versus the delta, the difference in repeat units, or versus the average peak height if we have calculated that previously. We can plot the locus balance versus the height or the average peak height. So we press the HP versus the height button and then open up the R GUI. Okay, so here we have the plot. It's the mean peak height on the x-axis and the allele peak height ratio on the y-axis. We will close this and we save as image. Heterozygous balance by by height. Save. Then we plot the locus balance. So now you see that it's quite close to the optimal for a 17 locus kit. The optimum inter-locus balance is 1/17, so it's close to 6% or 0.06. So you see that this is over amplified and this is a little bit under amplified, and this perhaps I will just save this as an image. I write locus balance and height. Save. Okay, so I close this window. Now we can summarize the data. Select the balance result. In this case we want to calculate the lower bound. So we calculate the 5th percentile. That means that only 5% of the data lies below the value, the calculated value. And we calculate on a per locus basis. So summarize. Now we can look at the data. And we get a table with a marker, the number of calculated heterozygous balances, the minimum, the mean, standard deviation, and the 5th percentile value. Also we get the number of calculated locus balances, the minimum, mean, standard deviation, and the 5th percentile. So here we can easily find out which loci is the least and the most balanced by right click on this column and sort. So we see that the least balanced loci is the SC33 marker, and the most balanced is the amylogenin or the VWA. Close this window. Okay, so that's the balance and the stutter ratios. Now I will go back to the edit. We want to calculate the precision, so we need to go back to the trim button and select our source dataset. And now we only want to look at the allelic ladders, so I will type ladder, and we want to keep the sample name, the marker, die perhaps, allele, and size. I will save this as validation ladder and press trim. Now we can slim the data. So we find the validation ladder and we accept the default. Same. Go to the precision tab, click the plot button, select slim dataset. Now I have only extracted the size, so I can only use the plot by size option, but we can also extract the height or the data point and plot by that instead. And we can select plotting a box plot or dot plot. So I will just show you how to plot the box plot of the size. So I press this and we look at the result. Okay, so here you have the allele on the x-axis for each marker, and you have the deviation from the mean in base pair of the size of each fragment. So you have a small box plot here. This image looks a bit dark, so I will change some of the options. We will change the plot theme to black and white, and we can expand the data point options and select another color, for example blue, and I will replot. Okay, so I'm more happy with this, so I will save this data, save this image as precision, and save. And I will close this. Now there's also a summarize button here. I click this and select the dataset, filter by kit bins. So this means that all peaks that are not defined in the bins are discarded, and it's important to have the correct kit here. We also exclude virtual bins, since we only want this precision of the actual fragments in the ladder. Here we need to create a key from columns, so that means that we select here the marker and the allele. So the marker combined with the allele makes the unique key to calculate the precision for, and we want to calculate the precision for target column. You can select several if you have extracted the size, height and data point. You can put all of this in this field, but now we only have the size available here, so we'll double click the size and then just calculate. So I will show you how this summary look. Select the precision table. Now we have a column with marker, each fragment in the ladder, each allele, the minimum size, the maximum size, the mean, the number of observations, and the standard deviation. Finally, I will show you how to clean up the workspace. So now we have this that we don't need because we only work with the slim format. We can select this and remove it, and we can select this and rename it if we would like to. So I will call it only validation ladder and slim. I want to remove the slim and only call it validation ladder. Okay, now it's renamed. We can remove the raw data if we don't need it because it's quite large. Remove, and everything else is things we want to keep. Now we can save our project. Press the save button and locate the folder you want to save in. Press OK. Type a name, validation project. Press OK and wait for the confirmation dialog, because if you have a large project it can take a while before everything is saved. Okay, now we can close the STR-validator software, and we can also close the R GUI. just say no to save workspace. Okay, so in our validation folder we have everything that we need: the precision data, plots, height, validation results for the stutters, and so on. And we have the most important, we have all the data stored in the project file, and this can be opened in STR-validator, and you can continue to work with it. Okay, so this is all, and the software I have used in this demo is the STR-validator package version 1.2, and of course you need to install R first, and there's more information about the package on this site. I have used Notepad++ to view the exported data from GeneMapper. LibreOffice is a free alternative to Microsoft Excel. For screen recorder I have used HyperCam 2, and to view the plots and this presentation I've used Adobe Reader. Okay, thank you for listening.